Good morning, class. So we're on day 28 of our Coronication, and we are studying magnets, electromagnetic force. And today I'm going to have you follow along with me by taking some notes on loose leaf paper or notebook paper, whatever you have laying around. So we're going to go through this PowerPoint, and I'm going to demonstrate you some labs. And if you have materials at home that you can replicate these labs, go ahead and grab your materials and your notebook and a pencil or paper writing utensil. And then you can follow along, or otherwise just follow along as I demonstrate some of these things and go ahead and take notes as we go through all of this. So I do want to say in the Google Classroom, I really appreciate everyone that has participated in the survey. So it helps me with my teaching and how this is going, and it helps me improve to show me what you like and what motivates you, because I don't have you guys in front of me. I really miss you, and it helps me understand what you're getting and what you're not getting. So feedback that I heard is that I need to slow down and explain things a little bit more. Some of you don't have the materials at home that you need in order to replicate these demonstrations. And that's okay. If you can't see a way to do it, if you can't figure out a way to do it with the materials that you have, that's fine. You can look for demonstrations on YouTube besides mine. You can also make stuff up. I mean, this whole thing is about magnets. Refrigerator magnets work the same way. So just grab whatever you have, be creative, and try and figure out how you can replicate some of these things without having the same materials that I do. The other thing is that I heard is that a lot of people would like to do some Zoom classes. And so I think on Friday, I will send out an invitation to do a Zoom class. Friday is the designated science day. So I will try not to interfere. If you have a 6th grade sibling, I know that 6th grade might have a science Zoom meeting. So I'm going to set up a different time. So look for that invitation in the Google Classroom, and we'll do some experiments together, or we'll just hang out. It'll be a Science Friday, and we can talk about some different things that you might be interested in. So come join me for that. Look for that invitation. So today we're going to be continuing talking about force and what magnets have to do with that. So where we left off is we had done this slide. We talked about what happens when a magnet comes close to another magnet. So they interact together. So depending on the poles, you either have an attractive force where they're together, or you have a repelling force, depending on which way the poles are aligned. So in this case, since they're repelling, I know I have two of the same poles. They could be a north pole or a south pole. All right, so there is a push force. And if I turn this magnet around, then it's an attractive force, and they have opposite poles. That's what attracts. Number 2, what's a magnetic field? So that's the region around a magnet where the force can be detected. And this is kind of what we're going to play with today, how we determine the strength of a magnetic field. So if we're here, like I can't feel a force. But the closer I get, there, I feel a pushback, right? And so I know my magnetic force comes out here around the magnet, and that's where that magnetic field extends to. And then number 3, what is a force? It's a push or a pull. So we talked about that. We measure that in newtons. All right. And so when a magnetic object is in a magnetic field, so 2 magnets or a paper clip, right? When it's within the field, the force exerted on the object has the potential to make it move. So if I just hold onto this magnet really lightly, I can make the magnet. I can make the paperclip move with the magnet. So the potential to make it move, okay, the amount of that force, okay, that potential is magnetic potential energy. So when it actually moves, that's kinetic energy, but the ability, the potential to make it move is the potential energy that this magnet, but that the magnetic force has. So our focus question for today is, what factors can affect the force of attraction between magnets? So we're going to set up a lab. We're going to set up this lab. So we're going to place one magnet in a cup. So I got my cup like this. All right. And we're going to put another cup on top of it. And it's going to create like a sandwich. All right. And we're going to have this magnet on a post. So you can think of a creative way to have a setup like this. Plastic or paper cups are probably not that hard to come by, with a refrigerator magnet in between there. And then if you have another refrigerator magnet, you could hot glue or tape, or you could actually simply just tie a string around it, around the magnet itself, and have that pull. So I'll put that here. I'll also make my screen just a little bit bigger here. All right, so I've got that. Okay, I have this, right? So second part of that says test the magnet on a post to see if it is attracted. So it's not repelling, right? So we have this magnet here and it's not repelling, it's attracting. So we don't have to flip it the other way. So the question here is, how many newtons does it take to break the force between two magnets? So I've got my scale, my spring scale. Maybe you still have the spring scale that you made. All right, and I can turn it so I can see the newtons, or so you can see the newtons here. That, and then, oh, I can pull. All right, so if I do it fast, I'm not going to be able to see my newtons. So I'm going to have to do this slow. But first, let's talk about predictions. So what do you think will happen to the force of attraction? So how strong, okay, between your two magnets, if you put some distance between the magnets. So if it's not going to be just the cup between the two magnets, what if we extended that distance? Do you think that the force will get stronger, weaker, or stay the same? So here you can stop the video, and in the red, you can copy the text and fill in the blank. So when I increase the distance between the magnets, the force will increase, decrease. So the force will get stronger, the force will get weaker, or the force will stay the same. Then why do you think that will happen? Okay, so make your prediction now, and then we will go ahead and increase some distance. So the way we're going to do that is we're going to put spacers here in between the magnet and the cup. So our little spacers look like this, and we're going to put them underneath this magnet here inside the cup, and we're going to measure the force. We're going to see what happens. All right, and of course, the difference between science and screwing around, according to Adam Savage, is writing it down. So if you would like to do this data table, all right, so across the top I've got 5. You can just briefly sketch this into your notes. And down the sides we've got the number of spacers, and we're going to record the forces in newtons. and figure out the average. So go ahead and record this down. You can stop the video. And then I'm going to move through this kind of fast and type this data into the field as well. Let's see if I can do this by making my screen a little bigger. Okay, so it's going to move over. Okay, that's fine. So I have, I'm going to try and center this. I've got one spacer here. I've got the newtons adapted, turned towards me. And I'm going to pull, eek, pretty slow. So I'm at a half. I'm at 1 Newton. I'm at 1.2. All right, so that's trial 1. I'm going to type 1.2 newtons. And I'm not going to put the n behind it because I have my n's up at the top of my data table. All right, so trial number 2. Okay, so I'm at, oh, I didn't even make it to 1. It was like 0.9. Okay. Oh, you know what? Maybe it would help if I was following my own directions. And I need to flip the magnet around. Maybe this will make a difference. Maybe I need to do my trial over. There, I put the other cup inside like the directions said to do. All right, so no, that was like 1.6. All right, so 1.6. And then trial 3. Yeah, 1.3. 1.3. I'll come back and do my averages later. All right, spacers. Now I'm going to put one spacer in here. So I'm going to do this. I'm going to put it underneath the magnet. So now it's not just one magnet, it's one magnet and a spacer. Still sticks. That's good. You might have predicted that it will take less force. All right, so flip my thing over, get it all set here, and pull. There's 1.2. 1.2. Oh, not even like, all right, there's 0.5. There's 0.5. Jeez, that's a big difference, 0.5. And then hmm. 0.6. All right. Now I'm going to do 3, and I want you to fill in predictions for the you do a little bit later. All right. So I have one spacer in there. I'm going to add 2 more. I wonder, is it even going to stick? All right, so I got my 3 spacers in there. And I have the magnet in there backwards. Heavy sigh. It was repelling instead of attracting. All right, so now I've turned my magnet over and there's an attracting force. This isn't gonna take much, guys. All right. Oh, geez. I can't even get it picked up. All right. Let's see how I can edit it. 0.3. So 0.3. Trial 2. Okay, I'm watching my newtons. 0.3. Okay, last trial. 0.4. 0.4. Okay, so those are all in newtons. And then I'll pull up my calculator to figure out averages. I wonder why that's so big. Let me reduce this calculator down. Lovely. Okay, so I need to add 1.2 plus 1.6 plus 1.3 equals 4.1 divided by 3 trials, and that equals 1.36 repeating. So I'm going to go to the nearest tenth, and I'm going to type in 1.4 as my average. 1.4 newtons. Okay, so then clear this. For one spacer, it is 1.2 plus 0.5 plus 0.6, and then I divide by 3 equals 0.76 repeating. So I'm going to bump that up to 0.8. Okay, then you want to add up your predictions, or you could just do your average force here. And then I'll show you number 3, my calculator. 0.3 plus 0.3 plus 0.4 equals, divided by 3 equals 0.04 repeating. Oh, I don't think I did that right. Let's redo that. So 0.3 plus 0.3 plus 0.4 equals 1. Okay, divided by 3. Oh, we're going to get a third repeating. Okay, so we're going to do 0.3 as our thing. So if we're looking at this, we've got 1.4, 0.8. I might have predicted that this would be 0.5, maybe? If we split the difference, 0.5. Kind of in between there, 0.6. Okay, and then 0.3. So as the spacers increase, our average forces decrease. So the magnets are getting further away and our force is getting weaker, the force we need to pull the magnets apart. So let's discuss what happens to the force of attraction between two magnets as the distance between them changes. So what I want you to do is to draw a graph to show the relationship between the distance of magnets and the force of attraction between them. So you're going to do like the L graph with an X and a Y axis, right? I'm not sure if this video is going to convert, but you need a Y axis that goes up and down and an X axis that goes side to side, okay? You're going to show the relationship between the distance of magnets. So that will be increasing. The further away they get, that will increase. Then what happens to the force of attraction? So the independent variable goes on the x-axis. So that will be the distance. That's the thing we're controlling. That's the thing that's changing. And dependent upon that is the force of attraction before them. So here in the slide, it says share in the Google Classroom. So just draw the graph on your notes and continue on because there's some other things. And I'll have you take that picture sure and upload it to Google Classroom when we're all done, and we can take a look at that. So thinking a little deeper, we're going to change gears. We're going to talk about what happens to the force of attraction when you add more magnets. So we wanted to know the effect on the force, the magnetic force, when you spaced your magnets further apart, and we ran that experiment. And now we're thinking, what happens when you've got 2 magnets or 3 magnets or 4 magnets or 1,000,000 magnets? What happens then? So if you put 2 magnets together, do you think the force doubles? Seems reasonable, right? And if you put 2 magnets together, what happens to the magnetic field or that region, that area? Do you think it will stretch further out? Do you think it will have more pull? All right, so we're going to set up an experiment like this. So we're going to position a paperclip on a diagram. So what I did was I took a piece of paper, and I'll show you in a second. Okay, we're going to have a paperclip, and we're going to slowly sag the magnet closer and closer and closer to the paperclip, and we're going to record the position of the magnet when the paperclip jumped, when the paperclip moved. So that'll be our jump distance. And we'll collect the data in a table, okay, which you're going to record in your notes. Okay, and we're going to do this with 3 trials. We're going to record with 1 magnet, 2 magnets, 3 magnets, and 4 magnets. And guess what? You're going to be surprised, because I was surprised. So first we'll make a prediction. What will happen when the magnet comes close to the paperclip? Why do you think the paperclip will move? And what is the kind of energy that is based on an object's position? Yeah, so we talked about kinetic energy and potential energy. So what kind of energy is based on an object's position? Hint, hint, it's the other one. All right, so here is our recording sheet. Go ahead and stop the video and record this down. And then we're going to go through 3 trials with 1 magnet, 2 magnets, 3 magnets, and 4 magnets. Okay, and then I'm just going to jump ahead. Okay, so let me show you what mine is looking like. Okay, so this is adjusted down, and we'll do the average a little bit later. I'm just going to try and get it so I can see it and you can see it. And I also probably want to turn this around. Oh, and I can't put this on the computer because magnets. Okay. That'll mess up my computer. So let me try this. Okay. So I think I got it. And then here's my paperclip. Okay. And then instead of doing it on the table, I'm going to need to jot this down for my trials. Up here. Maybe I'll do it down here, and that'll be easier for me, and then I can transfer it there so that you can see how that works. Okay, so I've got 1 magnet, and I'm starting it at 50 millimeters, and I've got my paperclip. I'm going to try and put these at the same distance here, okay? So my paperclip edge is on 0, and I'm going to move it closer. So I'm at 40. See how slow I'm going? I'm at 30.
I'm at 20. So now I'm not really, oh, it was at 20. All right, so we got 20. Let's try that again. So 50, 40, 30, 25. That's 21. I'm at 21. Second trial, and then I got third trial. So I got 40, 30, 25, 20. Okay. So there's that. Okay, so I'm gonna keep my paperclip there. 3 trials, and now we're gonna do 2 magnets. Will it double? So if we were having that jump at 20s, maybe this will jump at 40s. So here's my 50, 45, 40, 35, nope, 30, 29, 28, 28 for my first trial. Okay, set that back. 50, 45, 40, 35. Oh, that was 31. Okay. And then my final trial, my third trial, we got 45, 40, 35, 31, 30. Oh, okay, so we got 30. All right, 3 magnets. Dun, dun, dun. Okay, so we went 20s, 30s, 40s. Maybe we'll do 40s. Let's see if that happens. So we've got 50, 45, 40, 39, 38, 37, 36, 35, 34, 33, 33. So that's not that big of a difference. And here's the surprise. Let's try that again. So let's try 1. All right, 50, 45, 40, 35. Oh, it went at 35. Okay. 50, 45, 40. And there's 36. Okay. And now 4 magnets. So we got 40, 36. Okay, so like the same. 45, 40, 39. So a little bit of a jump. 50, 45, 40, 39, 38, 38. Okay, fantastic. I have my data. I'm going to record it into the chart. So reduce this guy down and move it over. All right, so trial 1 was 20, 21, and 20. Trial 3 and 2 was 28, 31, 30. Trial 3 was 33, 35, 36. Oh, sorry, those are red because I was going to have you do this, but said it would be better to do this together. 36, so you could see the weirdness. 39, 38. Okay, so to calculate jump distance, I'm going to clear that. We're going to do 20 plus 21 plus 20 equals divided by 3 equals 20.3. We'll go to the nearest tenth here. Okay, for 2 magnets, we're going to do 28 plus 31 plus 30. Oops, 30 equals divided by 3 equals 29.6. So we can do 29.7. 7. Okay, so there was a big jump there. Okay, now this one with 3 magnets, you would expect it to jump by that much again. That might have been what you predicted. So if we look at our average, it didn't do that. 33 plus 35 plus 36, 104 divided by 3. We got 34.7. And then we go here, we've got 36 plus 39 plus 38 divided by 3, 37.7. 37.7. Yeah, so we're looking at our thing. This is a jump, a big jump, right? And just for fun, do the math here. We'll do 29.3 minus 29.7 equals, oh, that wasn't right. Sorry. 29.7 minus 20.3. And that was a jump of almost 4, 9.4. And then your next one, we've got 34.7 minus 29.7, a jump of 5. So it goes from a jump of almost 10 to a jump of 5, and then 37.7 minus 34.7, a jump of 3. So 10, 5, and 3. I did not see that coming. That was interesting. So here, I want you to draw a model of what happens to the magnetic field when multiple magnets are added together. So what you'll do is you can draw your magnet, and you can draw your magnetic field. So this is kind of where I'm going with that. Okay, like this one. All right. So I've got my donut magnet. I've got a magnetic field here. All right. Kind of like those iron shapes, right? So here's what I'm thinking. If we have more magnets, right, the magnetic field is bigger, right? And less magnets, the magnetic field is smaller. However, the more magnets we add, it really doesn't, like, that might be the difference between 1 and 2 magnets, but then, like, we don't have a whole lot of stronger. As a matter of fact, the more magnets we add, like, it still gets stronger, so we can indicate that by the magnetic field, like, getting out here further, but they're closer together. I would these lines closer together the more magnets you add on there. All right, so add that drawing to your notes, and then we'll share in the Google Classroom. You'll take a picture of this document. So let's talk about what's going on.
So what force was acting to prevent the paperclip from moving? So why didn't it jump right away? Why did you have this, like when it's 50 millimeters, it didn't jump right away. So the deal is, and if you watch carefully, sometimes the paperclip will, and so that's, some potential energy there. It's almost in there. So what force does it have to overcome? It's a force of friction. And so why did the clip eventually move? Because the magnetic field came into the area that the paperclip was and became strong enough to cause that paperclip to overcome friction. So is there any evidence of kinetic energy? Of course. Yep, when it jumps. There's your kinetic energy. Is there any evidence of potential energy? Oh, yeah. You can feel the tension build. Like the closer to it you get, the more tension there is. That's our potential energy. That's our stored energy. Okay. So what happened to the jump distance that the paperclip moved when you added more magnets? All right. So when you added more magnets, the jump distance, got further away. So I went from 20 millimeters with just one magnet to 30 millimeters two. And it didn't increase by many more increases, but it did increase. Okay. So what happened to the force of attraction when you added more magnets? It got stronger. So what evidence do you have that the force increased? The distance increased that would cause the magnet to jump. So instead of jumping at 20, it jumped at 30, jumped at 35, it jumped at 38. So it our distance could increase and still provide a force strong enough to overcome friction. And so here's the tricky question. Why do you think the force increased so much with the second magnet and only a little with the third and fourth magnet? So here's the trick. Okay, here's what I want to show you. Let me pull that down here. When I've got two magnets, I've got this magnet and this magnet combined, right? So I've got like this much magnet, right? Okay. But then it extends my magnetic field. I add a third one on, right? My magnetic field gets bigger. It extends this, and my magnetic field gets bigger, but the force gets bigger. Why? Because now, instead of two magnets being close together so much, now I've got the whole stinking thing. This magnet's further away. So while I am increasing my magnetic field, the strength, the force gets weaker because this magnet is further away. Just by two magnets, but it's further away. All right. So here we go. Thing for you to record. What happens if an object is very far from a magnet? What do you think? Okay, so if the paperclip is very far away from the magnet, what happens? The third and fourth magnet you added were further from the paperclip than the first few magnets. Are the effects of those magnets' magnetic fields on the paperclip as strong as the first magnets? No, we just discussed this. So I'd like you to record this down in your notes, this red part. When magnetic fields are added together, the force of attraction does what? Increases, decreases, stays the same. But the farther the magnets have blank effect on the force of attraction. So the farther magnets have a stronger effect on the force of attraction, a weaker effect, or the same effect on the force of attraction. So record those down, you'll take a picture. All right, so when you use two magnets side by side, what happens to the net magnetic force? It increased. Why? Well, it made the magnet more powerful. It extended the magnetic field a little bit more, but it also made that magnetic field stronger. And why didn't a third or fourth magnet have as strong of an effect? Further away. Okay, so distance does have an effect on magnetic force. So based on your model of your magnetic fields, how far do you think a paperclip would move if you used 5 magnets, 6, 7, 8? Okay, so you want to record your prediction on your notes. Okay, adding more magnets does what? And now you can go, and so like if you didn't have the materials to do this, you could do this. I got with me soon. You could do this within FOSWeb. So what I want you to do is to go into FOSWeb. All right. So, yep, I want to click log in. I want to sign in. Yep, go ahead and in. I want to do this one. Yeah, close. Multimedia. Adding magnets. Remember your FOSWeb login is MVMS Science, and your password is Wildcats with a capital W, an S, and a 1. So you can play around this and you see what happens, right? You can add magnets. There's 2 magnets, there's 3 magnets, there's 4 magnets, and you can slide this and watch until it jumps, and then you can record the distance. Oh, look, it did it for me. That's awesome. Record the distance. And record the distance. So much else has my average for me. Cool. So you can play around with that. How many magnets it will add? 1, 2. It's like 8. Yeah. So you can go ahead and play on that. Okay. I also want you to add to your notes what patterns you notice as you added more magnets. Why did you increase the for less and less? Of course, add model of magnetic fields. Representing today is those lines coming out from a magnet you might draw. And then this is also a question for you that you can do at home. Do all refrigerator magnets have the same strength of magnetic force? Design a method to test this force, then write your procedures and results so you can do this. So, ladies and gentlemen, until tomorrow, I will look to see your recorded notes and your activities in Google Classroom. Thanks a lot.